program? Well, we might want to say, for example, that if I give it a list of positive numbers, this program returns a list of numbers between 0 and 25. So this seems like a reasonable pre-post condition. The problem is that when I want to write this property, I'm kind of mixing two things. So I'm talking about lists. So I'm expressing a predicate over that essentially describes lists, but list of something particular, and that particular thing is integers. And the predicate I use to talk about these integers are predicates in linear arithmetic. So there are essentially two different things. There are predicates that describe the structure of the list, and predicates that describe the content of each node in the list. And there are many logics for describing the individual things. There are very good logics for strings, which I consider strings to be essentially sequence over finite alphabet. But there are no good decidable logics for describing sequences over arbitrary complex theories, like the linear integer or linear arithmetics we just saw. And one beautiful thing that happened a few years ago was that we basically had some people had this brilliant idea that like you can take propositional logic and make it modulo theory by basically integrating as atomic predicates arbitrary complex theories that you want to use. And this kind of changed a bit the game because we were suddenly able to combine things together and just have very powerful logics. And they also gave us a way to solve such logics. So today's talk is about this new logic called symbolic monadic second order logic over strings, or actually monadic second order logic over sequences, which is a decidable parametric logic for sequences. So essentially, we do the same paradigm shift that we did from SAT to SMT. We go from logic for strings to logics for list over arbitrary theories. So I hope I convinced you that we need such a logic. And I'm going to pick one such logic over strings, and I'm going to show you how you can make it over sequences. So how you pass from finite to complex alphabets. And I'll show you some issues that arise in this transformation. And finally, I hope I'll show you that it works. So the monadic second order logic over strings is a very nice logic. It's actually very pretty. So let's assume we have fixed finite alphabet. There are a set of kind of atomic propositions, in this case A and B. And in MSO, sometimes it's called MSO, sometimes it's called WS1S. There are variants that they mean slightly different things. But the core of the logic is that you have formulas of this form where you can quantify first-order variables that denote positions in the string. So each string has positions associated with it, which are numbers. And these quantified variables basically are instantiated with these numbers. So in this case, we say that there exist positions x and y, such that position x is smaller than y, so it comes before y. So we can talk about order of events. And x is labeled with an A, and y is labeled with a B. So this string is a model of this formula because these x and y are instantiation of these quantified variables. We also have second-order variables, which is why the logic is a second-order logic. But they're kind of restricted second-order variables because we can only talk about sets of positions and not relations. So this is the detail, but essentially, we can use this to describe the strings of even length. So a string of even length is a string in which there exists sets of position E and O, denoting even and odd, such that the position 0 belongs to E, the last position belongs to O, pretend that we have this magic constant last. Any position, for every position in even, the next position is an odd. So we are enforcing the first part of the alternation. And for every position in O that is not the last position, the next position is in even. And here we see another ingredient of the monadic second order logic, which is the successor operation. So we can reason about the next event, the next symbol. So why is this logic interesting? Well, there was this really beautiful result in 1960 by Buki that showed that essentially for every formula in this logic, you can build a finite state automaton that is equivalent to it. It has exactly the same strings. And for any finite automaton, you can build a formula in monadic second order logic. So the two were equivalent. Okay? And if you are a formal language person, When you find two things that have nothing to do with each other and they're equivalent, that's a good day. So essentially, this is an example, but let's see if I can convince you that actually Buki did this. The interesting conversion is the one from logic to the automata. The automata to logic is actually very easy. But to go from logic to automata, essentially Buki did what every computer scientist does. He did a construction that it was inductive. So he had a construction for individual predicates and showed how to basically use some combination operations of our automata to build the automaton for the whole formula. So I'm using DFA to describe deterministic finite automata. So for example, if you want to do the automaton for phi1 and phi2, you can take the automaton for phi1, the automaton for phi2, and just do a product construction and get their intersection. So this is very easy. But what about all this madness here? Like, what do we do with all these first-order variables, second-order variables? So there are a bunch of operations that they don't look like automata operations. So what Buki thought about is it was essentially a little trick where he did a change of alphabet to represent the content of the variables. So let me give you an example. So let's say that we have a formula that has three second-order variables that are free in the formula. So the variables are free variables. So they will have a denotation, which is essentially their content. And what Buki did is like, OK, let's build a DFA over a slightly different alphabet, where for each symbol, we also put a bit vector. And each bit at each position corresponds to whether that position belongs to the corresponding variable. Let's repeat an example. So let's say we have this string. This particular symbol, the pair 0, 1, 1b, means that this position does not belong to x0, because this is a 0, but it does belong to x1 and x2. So essentially, it's kind of a characteristic function of these second-order variables. And we will do the same thing for first-order variable with the only restriction that only one bit can be set to 1 throughout the whole thing, because first-order variables are a single position. So let's look at a concrete example of actually how to do the operation for one element of the logic, which is x2 equals x1 plus 1. This means that the two positions x2 and x1 happen one after the other. So for a while, you read a position that is neither x2 nor x1. Then you find position x1. Immediately after, you find position x2. And then, again, no x1, no x2 for a while. And here, really, the part that you have to observe is that this column here, every symbol that we can read with the transition has the first bit set to 1. And nowhere else the bit for the first position is set to 1. Here is the second bit that is set to 1. So basically, these transitions are encoding that we found position x1 and we found position x2. And 0 everywhere else. OK? And then the tricky part where the proof is really, it works, is that he found a way to get rid of the existential quantifier. At this point, we have a formula, let's say, with 3 free variables. But when we want to build the DFA for the formula for exist x2 phi, we will only have 2 free variables. So one column of the bit has to go away somehow. And Buki showed, look, in fact, you can just ignore the bit corresponding to the variable you're existentially quantifying. And guess what? You get a DFA that accepts the correct language. And this is very nice. It basically just builds on the fact that existential quantification can be viewed as non-determinism. You can read our paper or Buki paper to read about it, but it's very, very beautiful. In fact, what happens is that when you do this, you can introduce, you have a DFA over a different alphabet, but you can introduce non-determinism, and you might have to determinize. And if you have a formula that doesn't have free variables, this construction ends with an automaton over the original alphabet you had, because there are no bits at point. OK, so essentially what Buki had was a decision procedure for monadic second-order logic of one successor over strings. And because after we build the automaton, you can check MS. So now that I told you everything that I haven't done, I can tell you a little bit of what we've done. So we extended this logic to operate over sequences. And extending the logic for itself wasn't too complicated. So this is the example I showed before. And kind of, Buki already gave us a good logic. Lots of people gave us many other good logic. And essentially, all we needed to do to encode this logic was to use a good logic that already works and combine it with a parametric theory so that we could talk about things like linear arithmetic. So we're going to assume that we are given a background theory. And the background theory is essentially a pair where we have an alphabet sigma that can be potentially infinite. This is the content of our list. And we have a set of predicates over this alphabet sigma. For example, linear integer arithmetic. And the only thing we're going to touch in the string, we're going to change the syntax so that instead of having our unary predicates to be over elements of the alphabet sigma, there are going to be actual predicates in our background theory. So this means that position x has a content that satisfies the unary predicate phi, and we will see an example soon. But models are not over the predicates. The models are, of course, sequences in sigma star. So back to our example. What is in our logic, how do we express these predicates? Well, it's very easy. It's essentially, the first one says that for every position, the content of the position is a positive number. And we have this predicate here denoting the concept of being a positive number. And similar here, we have the numbers between 0 and 25. So this is the only change. That's it. Change the logic. What changes? Well, what changes is actually that by just doing this little change, so actually one thing I want to stress out I forgot, is that our set of predicates has to be closed under Boolean operations and has to be decidable. Like, we need to be able to check emptiness of a predicate. So now that you know this, we can see why this logic is a new interesting property that you don't have in the finite alpha case. And this property is that if you have the conjunction of two unary predicates, this is equivalent to moving the conjunction in the predicate, in the unary predicate itself. And this is, and similarly for negation. And this is because we have closure under Boolean operations. Okay? So one might wonder, is logic decidable? Because otherwise, it's just lots of symbols with no meaning. And the good news is that we can, in fact, convert these predicates in the logic directly to the logic that Buki gave us. And this is very simple. It's just we have, even though we have infinitely many predicates, for example, in the linear integer arithmetic, there are only finitely many in the formula that we are working with. So if you give me a formula, I can pick all the predicates that are in it, and say, are these 3 predicates? I can compute all the Boolean combinations that are satisfiable, and I can use those as a new alphabet that is finite, and I can use in the classic logic we saw before. The problem with this is that you get an exponential blow, because there are exponentially many such predicates in the worst case. So can we do better? So Buki did this very nice construction to finite automata. Can we have something similar and just solve our logic in a smart way? And the solution is this thing called symbolic automata, which are essentially similar to how our logic I gave you is modulo theory. These are automata modulo theory. So this is, for example, a formula in our new logic that says there exists 2 position x and y that come in this order, and the position x as a number greater than 0, and position y as a number smaller than 25. This is the symbolic automaton corresponding to it. So transitions are labeled with predicates, similar to what you have in here. These are the same predicates. It's the same alphabet. But one thing that I want to stress, and notice that the strings are still over sigma, even though we are using predicates. One thing that is interesting to observe is that some of the predicates we have in the automaton, they didn't exist in the formula we started with. These basically disappear because symbolic automata also use this property that predicates are closed are Boolean operations to compute these new predicates. So you can see the full construction in the paper. However, I'll give a bit of why using symbolic automata is a good idea. So remember, in the construction we saw before, we had to do all these explicit basic enumeration of all possible bit vectors. And with symbolic automata, you can represent this notion in an easier way by just using predicates themselves. So in particular, in this case, we will have a predicate over a pair of bit vectors and symbols in sigma. And we will use it to essentially just do the simplify the representation. And you basically get this simplified automata that just uses bit vectors. The case where this really shines is when, in fact, we have a predicate over that uses, this is the predicate for the unary, this is the automaton for the unary predicate. Here we say if the bit number 1 is 1, then phi needs to be satisfied. So this is really what you see, the symbolic automata are very natural of this. So does this work? Well, we change alphabet, and we're working over a new alphabet that was the Cartesian product of two alphabets. So the question is that still a decidable Boolean algebra? Is still a theory we can work with? And the good news is, yes, the Cartesian product of two algebras, of two decidable Boolean algebras, is also a decidable Boolean algebra. And one of the tricks is how do we implement it, and I realize I'm slightly running out of time. So we have essentially two implementations that are based on kind of a notion of binary decision diagram in some sense, but modulo theory. So the idea is just we use these decision diagrams to represent the Cartesian products where the nodes are elements of one algebra and the leaves are elements of the other algebra. So I cannot go much into detail, but think of a BDD modulo theory. And we have two versions of it, and I'm going to show you just quickly how these two versions work. So we implemented this logic and integrated it with D3. So we have all the parametric theories from SMT solvers, and we evaluated it on a lot of examples. And in particular, we show you two, one over finite alphabets and one over infinite alphabets. So we evaluated on a lot of formula over finite alphabets. Let me show you a couple. So what I want to show you here is that although our logic is modulo theory, it has comparable performance, even the finite alphabet, to a specialized implementation, which is Mona, which is over finite alphabets. So despite the generality, similar performance. What's interesting is that when we go to complex theories, and for example, here we generated random formulas over linear integer arithmetic, you get that if you wanted to do the translation I showed you from sequences to strings by basically taking all the Boolean combinations, you get that doesn't work. Because essentially, computing those combinations always is much slower than just building the symbolic automaton for the formula. I didn't go into much details, but the story is essentially building the symbolic automaton is better than building the minterms. So I'll conclude and just tell you a little bit more about what I showed you. So this logic, we haven't quite decided if we like this name. The monadic second-order logic or sequences is a new logic that extends the classic monadic second-order logic to be modulo theory. And we provided an effective decision procedures using symbolic automata. The logic completely subsumes the version of the finite alphabet while retaining similar performance. So it's essentially more at almost no cost. And there are a lot of interesting future directions for extending other logics in a similar fashion. And I invite you to see this page that I try to update as often as I can, where we have all the advances that are being made in the recent years, symbolic automata, symbolic logics, and symbolic everything. So thank you.
Okay, thank you, Boris. We have a few minutes for questions. Everyone seems to be.
It wasn't even after lunch.
So. Well, you did really well. You did really well. So I have one question.
Okay.
So why do you want to avoid this determinization if for symbolic automata you have such efficient integral? I mean, I guess determinization is not such a problem in the efficiency.
Well, I mean, determinization for symbolic automata is as hard as determinization for normal automata. Yeah. So one thing I didn't tell you is that this monadic second-order logic, even the classic one, has a bit of a high complexity, which is a tower of exponentials, the height of this house. So it's usually hard to make it scale, but determinization is essentially what causes it to not scale, and there are recent tricks that people have thought about for using alternation or using laziness to avoid this blow up. But
the other question I have, which I always ask you again,
as long as it doesn't start with co. Okay.
So, I mean, all these extensions to symbolic logic and symbolic automata seem to work all the time.
Almost.
And that's what's nice, right? You guys have all these secret papers that work, and it's great. It produces a lot of open paper, which is also good. What is it? I mean, what is it in the generic theory of symbolic automata and the languages they accept that makes them such nice extension of normal automata?
So that's what we thought at first, until we got 2 papers where things didn't work. So sometimes they don't work, unfortunately. And it's true that things work essentially all of the times in efficient ways. The part that is hard is how to exploit the Boolean structure of the basically structure of the alphabet theory to improve existing automata theory algorithms. Essentially, like in this case, the hard part was implementing this product algebra. And that never appeared in normal automata, like there was never need. So
but the things that didn't work, which I'm not sure.
So the things that didn't work, so for example, Marcus and I have another paper at TACAS appearing this year where you try to reduce the state space of non-deterministic automata. And when you make them non-deterministic symbolic automata, existing algorithms don't work. Like the existing data structure that people use for finite alphabet to make the algorithm n log n.
You mean union final?
No, there was, it's a sort of BDD in some sense, but you get n log n, but you get an exponential block in the number of transitions. So 10 log n to the n, which is not very cool.
Yeah, so but those are complexity questions. But if you just look at the fact that you get a language and that you get a decision procedure and so on, everything could be.
Yeah, no, there is another case, another paper where if you read multiple symbols at the same time, for normal automata, doesn't change because you can split transitions. For symbolic automata, everything becomes undecidable.
So you expect that this future direction will be 1 paper each?
No, I expect this is someone else will do it. That's what I expect.
Good. Okay, so let's move on to the next talk. I think I might have more questions for Loris. Otherwise, let's thank him for.